Solids. There are fundamentally two types of solids. The first is a crystalline solid, in which the particles are in a highly ordered state. The example shown is of silicon dioxide, SiO2. In the solid state, each silicon atom is bonded to 4 oxygen atoms, and each oxygen atom is bonded to 2 silicon atoms. So each unit of the solid has a silicon atom at the center of a tetrahedron. At the 4 corners of the tetrahedron are oxygen atoms, which are in 2 adjacent tetrahedra. This means there are 4 half atoms of oxygen, or 2 oxygen atoms in each unit. This unit is present both in crystalline solids and in amorphous solids. In the crystalline solid, all the rings in the solid are identical, 6 silicon atoms and 6 oxygen atoms alternating around the ring. This regular hexagonal structure at the atomic level is reflected in the macroscopic shape of the quartz crystal, which is also hexagonal. On the other hand, the amorphous solid has rings of varying sizes, from 4 to 8 atoms of silicon and oxygen in each ring in the given picture. The amorphous solid has the same units as the crystalline solid, a tetrahedron with a silicon atom in the middle and oxygen atoms at the corners, but the larger scale structure is absent in the amorphous solid. Amorphous silicon dioxide is glass. So the two types of solids differ primarily in whether there is large-scale order to the arrangement of the atoms. There are 4 types of crystalline solids: ionic, molecular, metallic, and covalent network. The table shows the types of forces and the types of particles in each type of solid. It also gives some examples and some of the properties of each type. Ionic solids are made of oppositely charged ions that are held together by their attractions to each other. This is an ionic bond. Molecular solids are composed of molecules. The atoms in a molecule are held together by covalent bonds. These molecules are held together by the intermolecular forces of dispersion, dipole-dipole attractions, and hydrogen bonding. We have already talked about both of these types of substances. Metallic solids are metal ions in a sea of electrons that are held together by the attraction between the ions and the delocalized electrons. We call it a metallic bond. Metals may be a single element, one type of atom, or an alloy, a number of different kinds of atoms. Covalent network solids are atoms held together by covalent bonds. So how is this different from the molecular solids? Covalent network solids can be thought of as one giant molecule. In the covalent network solid, the structure is a 3-dimensional arrangement of covalently bonded atoms. These solids are a huge network of covalent bonds, the strongest bonds we know. Diamond is shown on the left here, and it is a perfect example of this, as is silicon dioxide, the quartz crystals we saw a little while ago. Because of the strength of the covalent bonds and the large number of them, these substances tend to be very hard and have high melting points. In molecular substances, the covalent bonds are limited to a few atoms, with some things having a lot of atoms, and then they stop. These collections of atoms are held together by van der Waals forces. The example shown is graphite, another form of carbon. In graphite, carbon atoms are bonded in sp2 hybrids, which form a hexagonal planar structure that has a very large number of atoms. These planes have an extensive delocalized pi system, which produces very large dispersion forces because of its polarizability. The planes are not bonded to each other, so they can slide over each other easily. Because molecular substances are held together by the relatively weaker van der Waals forces, they tend to be softer and have lower melting points. Though in the case of graphite, the melting point is not lower, probably because of the very large dispersion forces. The last two sides split the previously shown table into two parts that can be seen better. The first part lists the unit particles and forces for each type of crystalline solid. And the last slide lists some important properties of each type of solid, as well as some examples.